on. So we're very excited. Heiner's going to tell us a bit more about rotation seismology.
Thank you very much. Thank you. Well, first of all, thank you for the invitation. I'm really thrilled to be here, first time in Toronto. Can you hear me well in the back? Thank you. And also, I want to invite you to interrupt me at any time. If you want to, you can scream and just ask a question. So please do that. So I'm a seismologist, originally a computational seismologist. That's what Kenya is also very much into. And today I'm going to talk more about something that I call this a second life, which is more in the direction of general ground motion observations. And this is also for students, a message. I will tell you a story that is about the nonlinearity of a life in science. Sometimes an accident happens, somebody comes into your office and your life changes, you do something completely new. And that's also part of the story today. So I'm a seismologist. I know there is quite a lot of physicists. So in seismology, our goal is ground motion data. This is our data. We have seismometer sensors standing around the world, and usually we try to invert or understand the structure of the Earth's interior or seismic sources. The story today will start from a very different viewpoint in line with kind of the story as it developed. And that's why there's the word geodesy and seismology in one title, which is quite unusual. There's a lot of collaborators here, and you see from these images, partly the talk will be about Earth's rotation as a whole, but then also about seismic sources, tracking seismic sources, and also show an example of, let's say, innovative ground motions that happen when a caldera collapses, like on the Hawaii. So, what will you hear? I will start explaining something about ring lasers. Ring lasers are instruments that use laser optics to measure the Earth's rotation as a whole, and also rotations related to seismic waves. And that will be one of the topics. And that's why you have seen these two names in the title. So that sparked basically a new field of rotational seismology some 20 years ago. And I will tell you a little bit why this is interesting for us. Just for those general physicists, normally a seismometer only measures up and down in two horizontal motions, right? Displacements or ground velocities. And we've come a long way. But I will make a point that the observation of the complete ground motion is an unsolved problem. And part of the story is actually these rotational motions. You can also call them tilt motions at the surface, but also twist. And by the way, the title rock and roll is because engineers are also calling these motions rocking, for rocking motions, and ground roll is also something in the oil industry they call this the Rayleigh waves. That's why it's a justified title, not just for fun. Okay, so let's get started with something kind of unrelated to seismology. First of all, as you all know, the Earth rotates around the rotational axis, and that axis is changing all the time. So you have, if you want the vector of rotation is something that wobbles, and the direction changes, and also the length of day changes. Even though you think, well, my day is always the same length, it's not like that at all. It's LOD. LOD, length of day changes, is something that's varying. You know, if you think of an ice skater, you know, when masses are further out, you're slower, and so forth. So that it is changing. Now, to observe that and to actually even orient the Earth in space, you need a reference system. That's geodesy. I'm not an expert in that. But the way Earth's rotation is measured today and is related to an inertial system and a coordinate system is by using VLBI, very long baseline interferometry. And that is a very, very complicated way of, let's say, approximately 10 stations around the world, changing every couple of minutes the orientation of the antenna towards the edge of the universe. Then you assume that you have a plane wave, and you can, it's like an array measurement with, like with your ears, you know where the energy comes from, the light energy, and you can orient yourself in space. Now that's very, very expensive. It has a low time resolution. Let's say of a couple of hours or a couple of days, you have to get all the data together and then analyze and get the Earth's rotation rate and the direction of the Earth's rotation vector. If you don't do that, geodesists tell me after a month, your GPS would be dozens of meters away. So more than 30 years ago, the dream was expressed, can you actually try to measure this ground-based from the Earth, not using this VLBI with a reference to the stellar objects. So that's the question that was posed, how to observe Earth's rotations from the ground. And that led to the so-called ring laser technology. So this is what I call, the nonlinear event in my life. This guy, Ulrich Schreiber, was called by science the Lord of the Rings, Lord of the Ring lasers. He came to my office probably in 2000, 2001 and told me, well, we're building this high-end ring laser system. I will explain what it measures. It actually measures the rotation around the vertical axis of this instrument. And this is here, the border to the Czech Republic in Germany, very stable igneous rocks. And this is part, this antenna is part of the VLBI measurement as well. So that was the starting point. Later, I will talk about a 4-component ring laser that we installed near Munich. So this is only one component of the rotation vector. But even with this one component of the rotation vector, you can do a lot of interesting things. So how does a ring laser work? This is an animation that was made by science. So you have basically a vacuum cavity. So these are tubes. So in our case, this would be actually 12-meter side length of this triangular structure. You send laser, monochromatic laser, one direction, the other direction. Speak fast because so if this rotates, this triangle, then one of the because of the speed of light doesn't change, one of the lights beams will have a slightly longer path than the other one. So because C is constant, you have a slightly different wavelength. They superimpose and you get a beating. You get a beating frequency, and that's the Sagnac frequency. And that beating frequency is directly proportional to the rotation rate around the vertical axis of this instrument. So that's, in a nutshell, the principle of the ring laser. So actually, what we observe is a very boring, almost constant sinusoidal wave, which is the rotation of the Earth. Right? So that's basically always constant. It changes almost not at all. But if there's tiny changes, and this can be through an earthquake wave, seismic waves, that actually not only displace the ground, but it also does this, right? It also does this and this. So in this case, that's this twist motion. Let's call it a twist motion. It's a rotation around the vertical axis. So this is like FM radio. So it's the motion then is encoded as a frequency change in this sinusoidal motion, and you extract it with exactly the same mathematics. And that's your method that you encode, which is then our rotational seismogram. And that's what now here's an example. So this would be the constant Earth's rotation frequency. And then suddenly, this is for the Sumatra earthquake in December 2004. Suddenly, the ring laser measures this perturbation around the Earth's rotation. That does not mean the Earth's rotation changes, but it just means the ground locally rotates. Okay, so this is noise for the geodesist. And that's you probably all know this statement: one person's noise is another person's signal. This is what the guy told me. He comes into my office, say, we measure the Earth's rotation, but sometimes we have this noise. Do you want to work with this? And I mean, at the time, I was a computational seismologist. I didn't even know how a seismometer works, still don't know. So I called the godfather of seismology, of broadband seismology, and I told him, somebody asked me to work on rotation, and he said, put your hands off, don't touch it. And sometimes you have to go against the advice of older people. That's also a message, or you know. So it turned out to be an interesting story. So, by the way, seismology started exactly like that. It started as one person's noise is another person's signal. This is a graphic that is most of the seismology textbooks. In 1889, a guy called Robert Paschwitz in Potsdam, he was looking at gravity measurements, and you see the tides. And suddenly he saw this kind of strange signal as a perturbation of his tidal motions. And that was the beginning of global seismology. So this is not unusual. Okay, a little bit more detail. This is the so-called Sagnac equation. So what do we see here? This is the Sagnac frequency. This is this frequency that's measured by the ring laser. And it's a dot product between the vector of Earth, let's say, call it Earth rotation. This omega actually is, of course, primarily Earth's rotation, but it can also involve rotational motions by an earthquake. And it's a dot product with a surface normal. A is the surface normal of the ring laser, divided by lambda is the laser wavelength, and the perimeter. So geometry of the ring laser plays a role. To make it simple, the bigger the better. The resolution, the bigger the ring laser, the more accurate you measure the signal. So it's by the way, a very expensive way of measuring latitude, because you can imagine, you have if you're here at the North Pole, it's dot product is 1, and of course that also means if you are at the equator, you're perpendicular to it, you will not measure any signal. And there's a couple of numbers here that maybe are not important, but what is important is you're measuring down to rotation rates of sub-picoradians below 10 to the minus 12, 10 to the minus 13 radians per second. It's hard to get a feeling about that number. It's a small number. It's a very small signal, and that's also why it has not been observed in seismology. It's very, very hard to measure. Even though if you measure seismic waves, it's also, you're talking sub-nanometers, you're within an atomic radius, but it's just easier to measure. So this is basically what hot off the press, and I'm not gonna, this is with a ring laser, this is the red line is a VLBI derived length of day change. And the wiggly line here is a length of day change based on the ring laser. So that looks not very spectacular, but is actually very spectacular in the sense that the ring laser technology seems to be just now capable of directly measuring length of day changes. But that's from a geodesy point of view. So this was just one component, right? What I just showed. We wanted more, and so we have in Europe the European Research Council. So we actually asked, and we didn't even know how to do it. So this is a picture from the proposal. These are high-risk, high-gain proposals, and you can dream. You can ask, we want to do this. We don't even know how to do it, but please give us a lot of money. And this in this case worked. So in the end, it became this very, very complicated object. So I'm not sure you can see it from the back. This is a tetrahedral shaped object now. So there's 4 ring lasers of triangular shape, such that you can measure the full vector of rotation, full vector of Earth's rotation, and you have one for redundancy. It always helps. And actually, we added this redundancy component in the very end, and it was very important. This is an experimental physics project, and because you can imagine you're talking about nano precision, I did not think that we'll be able to actually build this and to get it right with the required geometric position, but in the end it worked. So you can see here, this is, the side length is 12 meters. So it was all excavated and built up basically from the bottom, just a few impressions from the construction. And this is now the inverted tip in the ground. So light comes down here, is reflected, goes up here in 3 triangles. And these are evacuated. So there's a vacuum in these tubes. And the big problem is actually to get the geometry right. And we explicitly used triangles for the first time, because as you all know, it's easier to define a plane with 3 points rather than 4 points. So again, here comes light, comes in here, goes out here. There's a window, and you can spot the mirror. And if you see a red dot, you can see that the laser is actually working. We use a green, so it's a 637 nanometer laser to get the geometrical path right and establish the optical path around. We use a very dangerous green laser that even just by looking at a point at the reflection point, you get headaches. So it's actually very dangerous and probably not allowed. But that's just what you see here with the green light. So this was the moment of first light when you adjust the mirrors, and suddenly, actually really suddenly you see the laser going around. That was a big moment. So this is the spot where you generate with the megahertz of the signals. You get the laser light to go around. And then in the end, you get 4 very boring sinusoidal signals. And this is when you see all the 4 rings are lasing, all the 4 rings show the Sagnac effect. And then from this, you can actually derive this full vector of rotation ground-based. And so again, I'm making a longer story short here. This is the current status of polar motion determination using this ring laser. And what you see here is if you want, this is in arc seconds, but it translates into 3 meters. If you want, this is the wobbling of the signal around the pole where the rotation axis is, and that's about 3 meters, right? So the polar motion, synthesized by the data, wobbles around by 3 meters. We would like it to wobble only by maybe 3 centimeters. So there are still 2 orders of magnitude missing. In theory, the ring laser should produce that, but it does not do that yet. But still, this is a world record. This is the most accurate synthesis of the full vector of Earth's rotation, and that's the current status as of 2 or 3 years ago. That, by the way, translates into an angular resolution of a football at a distance of 100 kilometers. So that's to some extent the accuracy. So this has been, I'm wrapping up the geodesy part here. So this is the most accurate direct observation of Earth's complete vector of rotation from the ground. The stability now is over 0.1 arc second, which translates into a polar motion of 3 meters. That still is not as accurate as we want, but again, it's a world record, and the ring laser people do know how to improve that to get to a better resolution. And this is 10 to the minus 7 of relative resolution of Earth's rotation rate. There are drifts that we see that are unwanted, can be from a coupling of this concrete structure, and the future will be in stabilizing these frequencies to get higher resolution. So that's basically the geodesy part. But what about seismology? So let me start by sort of categorizing the status of seismology. We have been observing with standard seismometers for a very long time that measure up and down motions and horizontal motions with so-called broadband sensors. And these sensors are so good that they did not need to be improved. They measure below the so-called noise level, background noise level on our planet. And at the moment, I would say there's a revolution going on in the way we observe ground motions. And I consider this as an axis that starts at a single point observation, goes to, let's say, billions of sensor points. And what I mean by that is, first of all, you have something like nodal seismology. These are these small sensors that you can just plug in the ground, and they record, and they may also communicate the signals autonomously. So, and they're relatively cheap. Also, all of your mobile phones have accelerometers. So they are also used, particularly in connection with strong ground motion. So if an earthquake happens, you know, it may be picked up, it may be identified as an earthquake-related motion and can be transferred into a database that can be used for, let's say, early warning problems. And then a very exciting new development, maybe some of you have heard about this, is so-called DAS, distributed acoustic sensing. It's a well-known technology, but not so much in seismology. What happens is you just take a classic fiber optic cable, and there is an interrogator, it's called, and you're sending light into that fiber optic cable. And because of impurities at each point and the cable, you get a reflection. And you always get it at the same time, more or less. You send a pulse, you get it back. Now, if there are two reflection points along the cable and they move towards each other, then these two reflection points are moving in time. And that basically gives you a strain measurement. Strain is the derivative, it's the gradient of the displacement. And the word gradient will play an important role. You're all physicists, you know what gradients are. It's the derivative of a vector field, or in our case, it's the derivative of a vector field, which is the displacement. And so here you're measuring one part, which is a diagonal element of the strain. Okay, so epsilon xx, which is the derivative of the displacement along that axis. Now, on the other side, in terms of a single point measurements, I mentioned at the very beginning, I think, the measurement of the complete ground motion is an unsolved problem. Why? Because a deformable medium not only has a translation, it has a rotation, and it also has a strain component. So whether we need that is another question, but it's the complete motion of the ground is currently not being observed. And the three components of rotation is, let's say, a first step into the complete observation of that, or the observation of the complete ground motion. And that's basically what we are working on, is trying to get the most accurate possible ground motion, including rotations. This is why you know, we're now entering the field of seismology. Now, what I just said here, with a little bit more with equations, if you basically make a Taylor expansion of this is U is our displacement field that we measure. This is this ground motion, or the motion inside the Earth. Displacement as a function of x, vector x, everywhere, and time. Okay, it's a vector, time-dependent vector field. So the Taylor expansion leads basically to something like this. And so you have U of x, which is one part that's measured with a seismometer. But then you also have a strain acting on a differential vector, and the rotation acting on a differential vector. You may have seen this before in mechanics. So this is the strain tensor, proportional to the spatial derivatives of the displacement field. And you have the rotation, which in this form actually is a rigid body rotation. What we actually observe with our rotation sensor, with a ring laser, is the curl of the wavefield. Very simple, okay? Curl of the wavefield, which is, again, proportional to the gradient of the wavefield. Space derivatives, that also means, that's a detail that you could derive these things also from a seismic array. So just to be on the same page, we want to go from measuring these three components of ground velocity, that's usually what's measured in a standard seismometer, to also measuring three components of rotations. That's where we want to head. And just a very simple equation that should highlight why this becomes interesting. So very simple. Let's assume we have a displacement uy, that's called a horizontal displacement, transversal wave propagating in x direction with waveform f. Then it has kx minus omega t. K is the wave number vector, x is position, omega is the frequency, t is time. And phase velocity is omega divided by k, is lambda divided by t. That's high school physics. Now let's take the second time derivative of that, and we obtain acceleration. Okay, so you get omega square in front, just 2 times this, and you get the second derivative of that waveform. Okay, nothing magic here. Now let's take the curl. So the curl, we take the curl of the velocity here. So this would be the vector 0 uy 0. That's the vector of displacement in velocity. And if you take the curl of this, you obtain a vertical component. This is exactly that of the rotation with a factor of -1.5 k omega and this f double prime. So interesting. The acceleration and this rotation rate has the same waveform. And now comes the point. If you divide now the amplitude of the acceleration by this, you get 2 times the phase velocity. Now that's very interesting, because by combining these two observations, you get direct access to the phase, to the wave velocity, the way the propagation below your feet. And it's a little bit, think of, it's like otherwise you can only get this through an array measurement. This is like with our ears, we have 2 ears. Why? Because, we want to get the direction of a signal. What our brain cannot do is give you the velocity. But let's say this sensor, this point sensor, point measurement gives you directly the velocity of a sound that comes from somewhere. And that's very, very powerful. And that will be exploited in the future. So, in simple terms, let's say the black trace would be your acceleration measurement with a standard seismometer. The red trace would be your rotation measurement. Take the amplitude ratio and you get phase velocity. So does that work with real data? Yes, it does. So here's an example at the top. So this is with the ROMY ring laser, this expensive instrument. This is a record of a Papua New Guinea earthquake in 2019. So the black line is the classic transverse acceleration from a seismometer. And the red line is the rotation rate in vertical direction observed with a ring laser with a completely different physical principle, optics and so forth. And you can see what we derive theoretically for a monochromatic wave works here also for a very broadband signal. So you can see they match almost perfectly well. The correlation coefficient is 0.99. So that allows you to do is to now say, okay, I go along the seismogram and calculate the phase velocity in some time window, and that's basically done in the bottom here. So this is the velocity of the waves that come from a certain direction. And here, these are for the physicists. These are surface waves that propagate along the surface. And we see here dispersion. That means actually you can see by the eye the periods are longer here, lower frequencies. Periods are smaller here, high frequencies. And you see dispersion. Dispersion means the frequency dependence of velocity. And this is very important information in seismology. It allows you to derive depth-dependent seismic velocity models. Another thing is that we can uniquely derive from a point measurement the direction where the energy comes from. So this is done here in this plot. along the seismogram, we determine the maximum likelihood where the energy comes from, where it's the black dots basically indicate this is where the energy comes from, and the blue line is the theoretical back azimuth. So the energy really comes from here, and you can see that works very well. So all this from a point measurement. Otherwise, this would only be possible with a seismic array. So basically, we can summarize that such a 6, I say plus because you can also do this with strain, such a 60 degree of freedom point observation provides wavefield information similar to a small-scale seismic array in terms of slowness, back azimuth, and also phase separation. That means P and S wave can be separated, Love and Rayleigh waves can be separated. That has been nicely derived by other people. That's not something we discovered. Even in 1903, somebody wrote this down, and without any good seismometers on Earth, he said, "Oh, wouldn't that be great if we could measure these two things at the same time?" So I'm glad that a colleague of mine, pointed me out. We don't read these books. Pointing out that look at this in 1903, somebody has done that, but this was not done with real data today. So yes. Okay, so here we're basically applying this equation here. So we're just taking a ratio in a time window of the peak amplitudes. Actually, what we do is we just make a plot of rotation rate versus acceleration, put a line, and so the question here is whether it is phase or group velocity. Okay, it's a very good question. So if you think of this graph here, if you assume a certain you measure two horizontal components, okay, there's only one rotational component here. So if you think of if you now ask the question where does the energy come from, you would say you make a projection of the horizontal motion. And actually, at some point, the amplitude will be 0 because the wave comes from here. It's a horizontal wave, and there is no component. So it's the 90-degree direction that's uniquely defined. And from that, you can very precisely get the vector of where the energy comes from. With real data, it's much more simple because you can actually maximize the cross-correlation coefficient as a function of direction. Because of scattering, it will be maximum in the direction where the energy comes from. But in theory, it's only the null vector that actually allows us to do that. Does that answer your question? Okay, so we will use this actually later in a very nice application. So the point I want to make, this has a lot of potential applications. And one is measuring rotations on the seafloor, because all the ocean bottom sensors are tilted by waves. And this every seismometer is tilt contaminated. So you can remove that and get this better. InSight, there's probably heard about the InSight project on Mars. Imagine now if you had a rotation sensor on Mars and you could directly measure the velocities by this amplitude ratio. It was much too late for Mars, but all the InSight team was quite hot on this idea. And so we have already a project with this team adapting this technology to planetary applications. Because, again, if you cannot afford a seismic array, which on planets is the case, it makes sense to have these additional wave motion components. Volcanology, source inversion, earthquake engineering, so the building vibrations, and I will talk about one-dimensional inversion and also glacial movements. All these things could benefit from these new motion types. So, of course, we cannot put a ring laser somewhere in the field. We have tried for a long time to convince a company to build a sensor that is capable of measuring rotations at the required resolution for seismology. And in 2016, the company called IXBlue, which is now, it was bought by another company, decided to, at their own risk, develop such a sensor for us. And that's the blue size. And what you see here is just a verification that it actually measures the right thing. I mentioned you can array-derived rotation. And this is an example from an earthquake observed in Taiwan. The red line here is the blue size observation, and the black line is an array-derived rotation. And there is no amplitude cosmetics here. It's absolute amplitude. So it really measures the right thing, which is very, very exciting for us. Now, let me go just in the last couple of minutes through one of the potential applications of using this so-called 6-component sensor. So this is downtown Munich when the Oktoberfest takes place. And we actually, when this does not take place, you have this big flat and you can do seismic experiments there. So one of the things we just talked about this over lunch is there's a lot of geothermal projects in Munich. Suddenly, this is a very aseismic area. Suddenly, you have induced seismic events in this region. And so it is important to understand this near-surface structure because that is amplifying ground motions. It's a sedimentary basin that is, may lead to increased risk of ground motion induced damage. So what you want to do is you want to get the local one-dimensional velocity, seismic velocity structure. And so you can do this now with such a setup, a single 6-component site. So this is a small seismometer, and this is the rotation sensor, blue size, installed somewhere in Munich. And what you do is you basically measure the noise, the human-generated anthropogenic noise for a couple of hours. And if you take the spectrum, that's something what you see in acceleration. 3 components of acceleration here. You see at frequencies between 1 and 10 hertz. It goes down, so there's a high frequencies in this area, like above 10 hertz, and then it goes down. And here in the rotation, you can also see energy here above 10 hertz, and then at 5 hertz, you're already entering the instrument noise level. So we would like to have this to be more sensitive, but this is the limitation. So at least in this area here, you can, if you want, simply to take a spectral ratio, and then you get the so-called dispersion relation that for surface waves. We're assuming that you have surface waves, and from that, you can then invert a one-dimensional velocity model. You can see the scales here. That's 0 to like 100 meters. That's depth. That's p velocity. That's s velocity. They are related. And so this is probabilistic. And let's say the yellow line would be the most likely one-dimensional model that comes out of the data from the single-point measurement. And we're lucky there is a borehole that we can sort of ground truth with, and the lithological changes that you can see here and here indicate that what we get from the data is compatible with what we see from a borehole. So that's very encouraging. Now there was a question already on the direction of that we get from a single point measurement. Now. I gave this problem to a master's student once. He came up with this beautiful animation. Let's say put seismic sources along here. This could be an earthquake scenario. So an earthquake starts rupturing and then maybe also jumps to another fault and jumps back to another fault. This is indeed something that is happening. Now, because if we have multi-component sensing here, we can uniquely take out along the seismogram the direction of propagation from the waves. The question was, can you backtrack if you want the seismic source? And it seems to work very well. when I saw this, I thought, okay, that looks very nice, and we wrote a paper and it got rejected and saying that, well, it's a nice idea, but there's no data. So at the time, my postdoc, Yuan, who's actually now at the Colorado School of Mines, he said, well, during night, we see this bursts of energy in the ring laser. And we also see it correlates well with data on the seismometer. So this is ring laser data. So that's actually, again, the vertical component, which is only shear waves. And this is the seismometer. This is two components, east and north, horizontal components. And if you see something like that, you say, well, it's the same origin. So now, what we did is he tried to derive the direction as a function of time, and I think there is a zoom in. So if we zoom into these data, you can see that if you estimate back azimuth, there's energy starting here at 100 degrees. So this is from north. So it starts here and goes over north, and goes back to sort of in the direction of northwest. And we have, to make a long story short, we always thought this has to be the train. That's like 2 kilometers away, but it's actually cars. It's cars going along the observatory. And again, when I saw this, I couldn't believe it. And I said, let's try and check whether that's right and put a small seismic array and compare with F-classic, we call it frequency wave number analysis. And it turned out to be correct. And so here we're actually tracking cars, and we can determine their velocity, and it's in the right order of magnitude. So you could use this basically to check the speed of these cars. So of course, we don't want to do this with cars. We want to do this with earthquakes, because like in the earthquakes of the size of what we see in Turkey, usually we have ruptures that propagate potentially a couple of minutes over very long distances. Exactly. So we want to turn this into a business, so there will be a spin-off, and yes. We're poor scientists. We need to find other sources of energy. I play music in the streets. That also helps sometimes. Okay, the last example, a caldera collapse, quite spectacular. This is in Hawaii, Kilauea. So this was like a before and after picture. So maybe some of you, I've been there a long time ago. This is the parking spot here. You usually came around here and parked here and then walked around. And so, okay, this is where the parking spot was. So this is completely gone. An absolutely spectacular caldera collapse here. If you look at the numbers, this is in meters. So this is before, and this is about 500 meter in altitude drop. And this happens in like daily magnitude 5 earthquakes. It's like the rim is doing this, it's going down. And my colleague from Munich, Joachim Wassermann, he installed a rotation sensor here in this observatory, just right here, at the time when this happened. So this was some of the first observations. This is what we wanted. We have 3 components measured with the seismometer here, and these are now 3 components of rotations. And because it's an optical sensor, you can easily integrate from rotation rate to rotation. And what you then see is, we would have to go into detail, but what you then see is a static rotation. So this is what happens also when you have a large earthquake. You have strong motions, and then afterwards the Earth is different. It's tilted. And that's also why a broadband sensor then looks like it's continuing moving, because it has an offset. So this is the first time that we could measure not only a static displacement, but also a static rotation. And this, of course, will help to actually understand what the source does. So it's a new type of observation that we have. So what I didn't show here, now this is a couple of other potential applications, is We correct for the tilt contamination in ocean bottom sensors or in strong ground motions. Actually, this amplitude ratio measurement allows you to basically do tomography without travel times because you get the information from the amplitude ratios. We're just applying this in planetary applications. I have one more slide on that. Also for structural health monitoring, we've managed to already show that if you have measured it in a concrete bridge and it gets damaged, we observe the same velocity change than we do with other types of techniques. There is a benefit for source inversion. We've talked about this briefly, and moment tensor and finite source inversion. So that has been the nice aspect of this kind of new field, is it has applications in a very wide range of fields. Now, so an outlook, we're in the process of we have a proposal running trying to design experiments for moon seismic experiments where we include rotation sensors or DAS, also gradient type of sensing. So that's an exciting new direction because, as you probably know, there's a hype in going to the moon. There will be actually the second prototype for the InSight sensor will go to the moon in 2025, if I understand correctly. So that's an exciting new frontier. And another very interesting new application is this is a top view of a mountain ridge, the highest mountain in Germany, 3,000 meters. We have a sensor here. This is an environmental research station. It's the Zugspitze. And what you see here is from a single seismometer through autocorrelation technique derived velocity, seismic velocity change in the surrounding of that medium, single seismometer. And what you see is the velocity is actually slowly, you get a seasonal, this is over 15 years. You get a seasonal variation here, but you can also see the velocity kind of continuously drops, and that's climate change. So that's the change of the permafrost boundary that is monitored there. And we are currently applying, observing this also with gradients. And by that gradient, I mean strain and rotations, because you can show mathematically that the gradient is actually much more sensitive to structural changes around near the receiver. So that's kind of environmental seismology, also a very interesting new research front. So to wrap up and conclude, ring lasers, the origin of that story, deliver now the most accurate sensing for geodesy and seismology. From a portable point of view, we managed to apply the fiber optic gyro principle and have a first new broadband sensor for seismology. That's the so-called Blue Size 3A family. And actually, the field studies with these sensors are just beginning. And there's a number of potential interesting applications that some of them I've talked about. If you're interested, there's a couple of links here to follow. We also have a YouTube channel with quite a few interesting movies to show. And by that, I want to thank you for your attention, and I'm happy to take your questions.